right, y'all, welcome back. Today we are going to continue learning how to solve equations that involve trigonometric functions. And we're just going to go over some different strategies. Today we're going to focus mostly on how we can use trigonometric identities to solve equations that have multiple different trig functions embedded in there. But there's one other equation that I want you to know how to solve before we get into all the identity stuff. And that is an equation like this, where we didn't see one like this in the last lesson, but it is possible that you have some stuff going on inside the parentheses here, as opposed to just having an x. And so you're going to solve it very similarly to how you would solve it if it was just x here. But there's one extra little step at the end that we have to do to get rid of this 1/3. So let's go through the steps here. The first thing we want to do is we want to divide both sides by 2. Okay, to basically reduce this 2 divided by 2 reduces to 1. And so then we're left with cosine. Oh, that's kind of small. Let's bring that a little bigger here. A little bigger. Okay, so cosine of 1/3 x now is equal to root 2 over 2. So here's where we're going to actually stop doing what we did before. And, and just take a minute to pause here. So we still want to get rid of this 1/3, but the thing is we can't really undo this until we undo the cosine. So we're going to just take a moment and actually find the angle measures around the unit circle where cosine is equal to root 2 over 2. So if I look at that unit circle, again, I'm looking for the x coordinates because we're dealing with cosine here. And so I see that there are angle measures at pi over 4 and 7 pi over 4. Both of those have an x value of root 2 over 2. Now, the big difference here is I haven't actually isolated x yet, but what I need to do is get rid of this cosine so that my next statement is going to be 1/3 x equals, and from here it'll kind of depend on what the directions say. Like we talked last time about whether the directions ask for just the solutions on the unit circle, if there's a restriction, or if it's going to ask for all the solutions. So I'll just show you how to get all the solutions, and then you only have to name the ones that are in the interval that's requested in the directions. So if I'm going to give the general solution here, I'm going to say that the angle measures at play here are going to be, what did I say they were? Pi over 4 and 7 pi over 4. So let me go ahead and write that out. Pi over 4 and 7 pi over 4. And we'll have that plus 2 pi n. And so the big question here is, need the pi, is how do I get rid of that 1/3? Well, we do that at the very end, okay? So the big sort of reveal here, the big trick is that if you've got stuff on the inside of the parentheses, when you're solving a trigonometric equation, you want to undo that after you find your angle measures. So from here, if I have 1/3 x, to get rid of this 1/3, I can think about it one of two ways. Either I can think, okay, we can divide everything by 1/3, or, which might be a little bit easier, is to multiply both sides by 3. Okay? Now you got to be careful here, and that's because I have to multiply the entire side by 3. And what I notice most students miss is that you actually have to multiply, oh gosh, that's a pretty ugly 3. You also have to multiply this little thing right here. And the reason for that is this is indicating the period for which our solution set's going to repeat. So like we'll get another solution set after 2 pi units. But if we have what is here, a horizontal stretch, that's going to change our period. Remember, we calculate the period by doing 2 pi over b. And so if we do 2 pi divided by 1/3, that would be the same thing as saying 6 pi. And so since our period is 6 pi, our solutions will differ by 6 pi units. So make sure you also do the multiplication to this thing too. Now that's pretty much it as far as a difference between this equation and any of the other equations we solved in the last unit. So if I multiply all these by 3, I'm just going to copy all this. I'm going to get 3 pi over 4 and 21 pi over 4 all plus 6 pi n. So basically I'm just multiplying each of these things by 3. Kind of like using the distributive property here. That's one way to think about it. Distributing the 3 here, here, and here. Okay. So, so that's how you're going to handle when you have a coefficient, or really just anything going on the inside of the parentheses here. If the directions ask you to only give me certain solutions, then you want to be a little careful about that. Like if this says, give me all the solutions that are between 0 and 2 pi, this guy right here is not between 0 and 2 pi because we multiplied it by 3. Now we got 21 pi over 4, which is greater than 2 pi, which would be 8 pi over 4. So you'd really only report back this one, this 3 pi over 4. That's the only one that's going to fall in that range. So just be careful when the directions restrict which solutions that you give me, that you only give me the ones that are actually in that interval. But this would be the general solution. This would be all of the solutions. So that's how we deal with, if you've got a coefficient on x, or if you got, other things going on in here, you need to undo that after you find the angle measures. So the rest of today is going to be focused on how we use trigonometric identities to solve equations. And so we'll use a bunch of these, and there's a lot of them. But just briefly, what an identity is an equation that's always true. So a real simple identity would be something like 2 equals 2. Right? Because 2 is always going to equal 2. Those two numbers are the same. But there are more complicated identities, and I say more complicated, but basically you can have an identity with a variable in it as long as it's true regardless of what x is. So an example might be something like, and I'll type this out as I say it just so you can kind of see what I'm talking about. If I say 2x plus 2x equals 4x, that's going to be true no matter what x is. If x was 1, then I get 2 plus 2 equals 4. If x is 2, and I get 4 plus 4 equals 8, and so forth. So this is an example of an identity. It's an equation which is true no matter what x is. And so we've got different identities that involve trig functions that we can use to make substitutions in our equation to solve. So today we're going to go over sort of 3 groups of identities: the reciprocal identities, the quotient identities, and what are known as the Pythagorean identities. So let's start with the reciprocal and the quotient identities. So the reciprocal identities are going to be ones that you're probably already a little familiar with. Basically what they do is relate the reciprocal functions to the original 3 trig functions. So for example, sine of x, or sine of theta, is going to be equal to 1 over cosecant of theta. Okay, they are reciprocal. So this is an identity. This is going to be true no matter what the angle measure is. Assuming that it doesn't that it's valid. You can't divide by 0 here, so there's going to be one little x. I guess infinitely many, but there's going to be some x values where this isn't true, but they're not going to be valid for this function anyway. So for all the x values in the domain of these functions, this will be an identity. Another one would be cosine of x equals 1 over secant of x. Right? Those are reciprocals as well. Third one would be tangent of x equals 1 over cotangent of x. And the reason why we're writing these out is because we want to be able to use these as tools to help us solve equations. So once we go over all the identities, we'll go back and see how does that apply to maybe some more complicated equations. We can also sort of rewrite these 3. I mean, these are really the only identities, reciprocal identities. But you can manipulate these algebraically to come up with sort of variations on the identity. Like I can rewrite this as cosecant of x equals 1 over sine of x. With a little bit of algebra, I can rewrite those. I can also say that secant of x is equal to 1 over cosine of x. And finally, I can say that cotangent of x equals 1 over tangent of x. Oh, not s, x. Got to make sure we're consistent with those variables. So these are the 6 reciprocal identities. And like I said, we're going to use these to solve equations. And not necessarily all of them. Sometimes we'll use some more than others. But the whole point is, if let's say our equation has a bunch of sines and then one little cosecant in there. What we can do is rewrite cosecant x as 1 over sine x. And then we have nothing but sines. And once your equation has all of the same trig function, it becomes a little bit easier to solve it. There's 2 quotient identities, and they're for tangent and cotangent. Now remember that tangent, when we evaluate tangent, we find the y-coordinate divided by the x-coordinate. Now the y-coordinate corresponds to sine, And the x-coordinate corresponds to cosine. So we can say that tangent of x is the ratio of sine to cosine. Okay, so like one strategy is to try to get everything in terms of sine and cosine. And so if you have a tangent stuck in there, you can rewrite it like this. Cotangent is going to be, you look at the x-coordinate divided by the y-coordinate. It's the reciprocal of tangent. So it follows that this would be equal to cosine x over sine x. So these are our reciprocal and quotient identities. These are statements that are always true for valid inputs into x. So no matter what value you plug into x, assuming it's in the domain, this will be true. Now, there are more identities. Okay, I know this is a lot. Now these should all be kind of familiar to you. The ones, these kind of all go back to what we talked about in terms of the unit circle and that sort of thing. Now there are more identities that aren't as obvious, but they're all kind of similar. So let's kind of go over what are known as Pythagorean identities. These are identities that you're going to want to have memorized, and they're going to not be immediately obvious. And we can go back and talk about the proofs behind these, like why are these true? But let me just kind of lay them all out up front. So the first one says that sine squared x plus cosine squared x equals 1. This one's probably the most obvious one. And when I say obvious, I mean kind of easy to explain. Go back, think about your unit circle and how we name, let's say we had an angle measure. We'll just call it angle measure x, okay? So if this is the angle measure x, this side length is equal to the cosine of x if the hypotenuse is 1, okay? So we have this little diagram. And so you can clearly see that this is just a variation on the Pythagorean theorem. A squared plus b squared equals c squared, or sine squared plus cosine squared equals 1 squared, which is 1. So that's kind of where this guy's coming from. And all these Pythagorean identities are really going to be just kind of variations on manipulating the Pythagorean theorem. So they're all going to look kind of like this. You're going to have like squared trig functions. And there's not too many. There's really only 3. So let me go through the other 2 as well. So the second one is going to be tangent squared theta, or tangent squared x, plus 1 equals secant squared theta. I keep saying theta, but I'm typing x. Just a little habit I have there. And then the last one is cotangent squared plus 1 equals cosecant squared. Now you're going to probably want to memorize these. I know I don't make you memorize too much in this course. There's a lot you have to understand. But as far as just like memorizing equations, not a whole lot of that. But I would definitely recommend that you memorize these 3. There are variations on these, just like how we were able to manipulate these 3 reciprocal identities to write them in maybe a more convenient way, depending on what your problem has. And we can rearrange these too. Like basically we can solve for either cosine squared or sine squared and get a variation on this equation. So like, if I were to solve for cosine squared here, cosine squared x would equal 1 minus sine squared x. Or if I solve for, say, sine x, I would get sine squared x equals 1 minus cosine squared x. And you might wonder at this point, like, well, why am I writing down all these variations? You just want to be prepared for, like, if I want to rewrite a cosine squared x in terms of sine, this is going to be what I use. And you don't want to have to, remember, okay, well, in other words, you don't want to remember every single little combination here. Just remember these ones in red, and then know that you can kind of play with them algebraically, move things around to get them to be what you need them to be. And once we start getting into the actual equations, I think that'll make a little bit more sense. So we could rearrange this one as well. If we solve for tangent squared x, we'd get tangent squared x equals secant squared x minus 1. And we would also get, let's see here. So if we solve for, I guess, 1, we would have 1 equals secant squared x minus tangent squared x. Alrighty. And then for this last one, we can rearrange this by solving for cotangent squared. And that would give me cosecant squared x minus 1. And similarly, we could rearrange for 1 and get 1 equals cosecant squared x minus, there we go, minus cotangent squared x. So this is it, okay? That's all the identities we're going to cover today. We've got these reciprocal identities, the quotient identities, now we've got these Pythagorean identities. And what I want to show you is how we can use these to solve more complicated equations. One last thing before we kind of get into these, I don't want you to just sort of accept that these are true. I don't want to go through like the entire proof of all these, but I'll just kind of show you how you would get one of them. And you don't need to know this proof. I just want to convince you that this is true. So this top one I think is the most obvious. It's the easiest to show really quick. But let's say we started with this and I divided both sides by cosine. Okay, so let's say I divide this whole side by cosine, and I divide, or also cosine squared rather, cosine squared x, and I divide this side by cosine squared x. If I do that, sine squared x over cosine squared x, as we saw above here, is equal to tangent squared x. So that would equal tangent squared x. Cosine squared x divided by cosine squared x would be 1, and then 1 over cosine squared x would be secant squared x. So it's not really much of a proof, but you can kind of see where this is coming from. And you could do something similar to create this other Pythagorean identity. It's just that instead of dividing cosine squared on both sides, you would divide sine squared on both sides. And so I just want to show you like why these are true based on the fact that this is true. Okay, so really the three key ones you want to remember here are right here, and know that all these other ones that I've typed in blue are just variations on that, just algebraically manipulating around. And really, when you really break it down, this one up here is sort of like, the mother of the rest of these, okay? Every single one of these other ones are really just an algebraic manipulation of this original equation. So that's kind of interesting. Okay, enough backstory. What we're going to do now is we're actually going to jump into some equations and see, okay, well, how can I use the identities that we've talked about to actually solve this? So like for this first one, notice how we've got a sine and a cosine in this function. It looks like, if you're just like looking at this really quickly, it looks like what we want to do is factor this, right? Because we got the squared and we got the linear term. Not really linear, but it's set up kind of like a 2x squared plus 3x minus 3. But the problem is these are not the same function. So it's like not x and x. It'd be like x and y, or like two different variables. So our factoring is not going to work sort of right out of the box here. And what we have to do is we've got to make sure that all of the trig functions are the same so that we can factor it. And so what we're going to do is we are going to rewrite this sine squared x in terms of cosine, okay, so that all we have is just straight cosines across the board. So we're going to have 2, and I'm just going to put parentheses here for a second, and that's what I'm going to fill in, is like instead of sine squared x, what is it equal to? But the rest of this should be the same. Okay, so the question is, what is sine squared x equal to? So I'm going to go back up to my identities and find one where I can rewrite sine in terms of cosine. And that's going to be this first Pythagorean identity. Sine squared x is equal to 1 minus cosine squared x. So I'm going to rewrite this as 1 minus cosine squared x. Okay. And now, once I simplify this, I'll have something that I can actually factor. So distributing the 2 here, is going to leave me with 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. And now I want to combine my like terms and just overall just kind of clean up what I've got here. Now, when you factor, factoring is a lot easier if your squared term is positive. So what I'm going to effectively do is I'm going to move everything to the other side and swap, like basically change all the signs. So before I do that, let's combine my like terms. So I got 2 minus 3, right? I've got these two terms that I want to combine. 2 minus 3 would be negative 1. And so right now I've got negative 2, stay consistent here. Negative 2 cosine squared x plus 3 cosine x and then minus 1. So now we've got it in standard form. But again, we want that square term to be positive. So you can approach it two different ways. One is you can like add 1, subtract 3 cosine x, add 2 cosine squared x. Basically just move everything from one side of the equation to the other. Or you could just multiply both sides by negative 1, which might be a little bit easier to think about. So I'm just going to do that. I'm going to multiply both sides by negative 1. You know, this one. And really the only reason I'm doing this is to make my factoring a tad bit easier. Multiplying both sides by negative 1. And so what I get is basically the same equation. Oops. But all the signs will be reversed. Okay, so I'll have positive 2, minus 3, positive 1. Now I can factor this, okay? So out to the side, I'm going to think about this equation, or this expression, 2x squared minus 3x plus 1, and think about how I'm going to factor that. I know it's going to be two sets of parentheses, two terms that multiply to give me 2x squared, it has to be 2x and x, and then two numbers that multiply to give me 1, it's either going to be positive 1, or negative 1, negative 1. And since my middle term is negative 3x, it has to be negative 1 and negative 1. So this would be the correct way to factor this expression. So similarly, I'm going to factor this like kind of in the same way here. But I have cosine x instead of x. So this will factor as 2 cosine x minus 1. And because I've got all these parentheses, I'm going to avoid putting the parentheses around the x here. Cosine x minus 1. Now I can kind of solve it, you know, how the same way we did the ones last time, which is I'm going to use the zero product property to set each one of these expressions equal to 0. So 2 cosine x minus 1 equals 0. And also cosine x minus 1 equals 0. And now I can solve each one of these. So for the first one, I'm going to add 1 and divide by 2. So I get cosine of x equals 1/2. And for the second one, I get cosine of x equals 1. So I'm going to look at my unit circle, and I'm going to find all of the places where the cosine value is 1 or the cosine value is 1/2. So let's pull up that unit circle here. So it looks like I've got x equals, I'm just going to stick with the general solution here, just so I can stay consistent. So the first one I'm noticing is pi over 3. And then what else do we have? So 1/2 or 1. Okay, so it's 1 at 0 actually. Okay, I skipped right over that. So 0, pi over 3, and then the last one's going to be 5 pi over 3. And then we'll have our 2 pi n to finish this off. All right, again, if all I ask for are the solutions on the unit circle, then you'll just list these three angle measures. All right, so that's it for that one. So this is an example of how we use the Pythagorean identity to solve an equation. Now, sometimes you can't really use the Pythagorean identities directly. So like if I want to write cosine in terms of sine or vice versa, I need it to be cosine squared or sine squared. So I can't really use this, the Pythagorean identities here unless it's squared. So one strategy we can use here to solve an equation like this is to square both sides. And this is something you probably did a little bit in Algebra 1 and 2. Particularly in Algebra 2, you might remember whenever you square both sides, sometimes you end up with what are known as extraneous solutions. So as we solve this, we might get a solution that's actually not really a solution. And so this is something you have to do no matter what the equation is, even if it has nothing to do with any of these trig functions. If you square both sides of an equation, you have to go back and check your solutions to make sure they actually work. Because in some cases, you'll end up with, like I said, extraneous solutions. So let's go ahead and square this. So cosine x plus 1 times cosine x plus 1. I'll write it out completely so you can kind of see where I'm going with this. Cosine x plus 1 times cosine x plus 1. Whenever you're squaring something, you're just multiplying it by itself. And then sine squared x is just sine squared x. So let's go ahead and multiply these together. We can FOIL this out or just use the distributive property. And we get cosine squared x plus 2 cosine x plus 1. Now, we don't want to have different trig functions in the same equation. We want them all to be the same. So we need to change the sign to be cosine. The reason why we don't want to go the other way is if we change this to sine, we're stuck with an extra cosine. So if I change this to be in terms of cosine, then I'll have nothing but cosines in here, and then I can start rearranging and then solve it the way you would normally do it. So let's start by rewriting sine squared x. If I go back up here, I can see that sine squared x is equal to 1 minus cosine squared x. So I'm going to replace sine squared x with this. All right, so I've got cosine squared x plus 2 cosine x plus 1 equals 1 minus cosine squared x. Now from here, we want to get everything onto one side so that we can go about our business in terms of factoring and doing whatever it is we need to do to solve the equation. So I'm going to add, first I guess I'll subtract 1 from both sides, knock these two out. So if I do minus 1 on both sides, this is 1 minus 1 is 0. Both of these will 0 out. Then I want to add cosine squared to both sides. Am I going to be able to spell this with the mouse? Oh gosh. Oh man, that's brutal. Okay, yeah. Plus cosine squared x on both sides. And we'll combine our like terms. Let's get back to actually typing this out. So cosine squared x plus cosine squared x is going to be 2 cosine squared x plus 2 cosine x. And then we don't have any 1s. Those go away. Equals 0. So from here, we can decide, do we need to factor it like traditional factoring, or can we factor out a GCF? And since I don't have a constant here, I can just factor out the GCF, which in this case would be 2 cosine x. And I'll be left with cosine x plus 1 as my other factor. We can then use what is known as the zero product property and set each of these factors equal to 0. Okay, so we can set that equal to 0. We can set this equal to 0. And so we get 2 times cosine of x equals 0. And cosine x plus 1 equals 0. We're going to solve each of these for cosine x. So here, if we divide both sides by 2, I get cosine x equals 0. And over here, I want to subtract 1. So I'm going to be looking on my unit circle for all of the locations where cosine of x is either 0 or negative 1. So let's pull that up. And it looks like, okay, cosine is going to be 0 at pi over 2 and 3 pi over 2. And then cosine will be negative 1 at pi. So we get 3 solutions here on the unit circle. We get pi, come on. Why isn't it put it in there. Oh, nope, wrong one. Sorry, guys. Okay, so there we go. Pi over 2, and then also pi is going to be coming from this negative 1, and then finally 3 pi over 2. And those would be our solutions if we were just picking the ones on the unit circle. Let me hide this unit circle so you can see the work. If we want to give all the solutions, then we would say, put those in set brackets and say plus 2 pi n. Okay, so this one takes a little bit of work, yeah? But the big different strategy here is you may have to square both sides to be able to solve it. Now, what we need to do really is we need to go back and make sure that these actually work. So I'm gonna take away my little box here because I'm not sure that all these solutions will work. So we need to check and make sure that none of these are extraneous. So what we want to do is actually plug these in and see if they're actually equal. So out to the side, this is where we're going to do our little check. Okay, so let's check this out. That is too small to see. Let's make it big. Check. Okay. So we'll check pi over 2. Okay, so is cosine of pi over 2 plus 1, is that equal to sine of pi over 2? Okay, we'll check that. The other thing we're going to check is, is it true for 3 pi over 2? Is it true for pi? Okay, so we'll check each one of these. Now, cosine of pi over 2, if you're not sure, look at your unit circle, but the cosine of pi over 2 is going to be 0. So this is going to be 0 plus 1 equals sine of pi over 2 is 1. So 0 plus 1, 1? Yeah, that checks out. Okay, so this one checks out. I think I deleted my other one. Oh, that's all right, I'll come back to it. Now let's check this. Cosine of 3 pi over 2. So just go back here. I'm not sure what happened there, but cosine of pi over 2 was 0, sine of pi over 2 was 1. Cosine of 3 pi over 2 is 0, sine of 3 pi over 2 is negative 1. So check this out. 0 plus 1 equals negative 1. Bzz, no, that one doesn't work. So we're going to get rid of this 3 pi over 2. We know that doesn't work. And then finally, we need to check the last one, which was pi. Not sure how that got deleted. Must have typed something by accident. Okay, cosine of pi is going to be negative 1, and sine of pi is 0. So negative 1 plus 1 is 0, so that checks out. So the only solutions here are going to be pi over 2 and pi, okay, plus 2 pi n. So we're going to get rid of that 3 pi over 2. That is what we call an extraneous solution. See if I can squeeze that in there. There we go. Yeah, this is called extraneous solution. And this will, you don't have to worry about this on every single problem that you solve. Only if you square both sides do you need to worry about that today. So if you don't square both sides, don't worry about it. I mean, you can always check to see if you got it right, but you won't really end up with any extraneous solutions unless you square both sides for the problems that we're solving today. Okay, so that's the end of that one. We got one more problem for you. How can we write the solutions? We can't find them on the unit circle. Okay, so let's say we're trying to solve this, and we're going to use a variety. Okay, so right now I'm noticing I got a secant and a tangent. So I'm going to rewrite secant using my Pythagorean identity. Okay, secant squared x is equal to tangent squared x plus 1. So I'm going to rewrite this as tangent squared x plus 1. Okay, that's the secant x. That's how I'm rewriting secant squared x minus 2 tangent of x equals 4. So what I'm going to do is kind of play with this a little bit. I'm going to move some things around so that I can actually solve this. It looks like this is going to turn into a factoring problem. So I'm going to subtract 4 from both sides. 1 minus 4 is negative 3. I'm also just going to rearrange slightly. I'm going to put my squared term first, and I'm going to put my non-squared term next, so minus 2 tangent x. And then I've got 1 minus 4 is negative 3. So here, from here, I'm going to try to factor. So think about how we would factor this. Okay. So we've got, like if we had something like x squared minus 2x minus 3, we're trying to find two values that add up to 3, or negative 3 and add up to 2, so that'd be negative 3 and 1. Yeah, you can come in, no worries. So that'd be negative 3 and positive 1. So anyway, that's how that would factor. And so we need to factor this in the same way. Here we go. So we get tangent x minus 3 and tangent x plus 1 equals 0. All right, so we'll use the zero product property and set each one of these equal to 0. Oh, let's try that again. So we get tangent of x minus 3 equals 0 and tangent of x minus 1 equals 0. So one of these we do not, one of these we can just solve using our unit circle, but one of these we're not going to find on the unit circle. So you could probably already see which one it's going to be. Now for tangent of x equals negative 1, that's going to be where your x and y coordinates are opposites, and that's going to happen at pi over 3 pi over 4. Let's see, let's double check on that unit circle. Yeah, there you go. You can see at 3 pi over 4 that the x and y are opposites. There we go. So 3 pi over 4. And the other one would be 7 pi over 4. So that's what we're getting for our solutions to tangent of x equals negative 1. But for this, we don't have an answer to that, okay? At least not on the unit circle. So what we have to do is we're going to use inverse trig functions to solve this out. So use, and this is only for when you can't use the unit circle, okay? So the inverse tangent of 3, it's only going to give us one of our solutions, and I'll show you how to find the second one. So this is something that you'll put into the calculator. Let's bring that up. Make sure you're in radians. We'll hit mode. Yep, we're in radians. So we're going to do the inverse tangent of 3. So we get about 1.2. All right, so x will equal 1.2. We'll say 50, I guess, is how it would simplify. Now that's going to be one of the solutions. To get the other one, we're going to have to add pi to this. So we have this, but we also have this plus pi. Okay, so we'll add pi to that. All right, and there's our other answer. All right, so now we've got all 4 of our solutions. All right, well, that's it for today. Y'all have a great day.